Welcome to the solutions to the momentum problem set, problems number 7 and 8. Let's jump right in with problem 7 here. We have a 0.030 kilogram bullet, so that's mass, is fired vertically at 200 meters per second, VO, into a 0.15 kilogram baseball, also mass, so we'll call this M2 and go back and label this one as M1. That is initially at rest. So the baseball's initial velocity is 0. The bullet embeds in the baseball. That's significant, as at some point we may end up combining the mass to solve the problem. How high does the combined bullet and baseball rise? So that's H after the collision. All right, so we start off with a diagram to help ourselves out here. We have our bullet whose initial velocity is 200 meters per second. Our baseball that has initial velocity of 0. And the bullet is going to stick inside the baseball, and we're looking for the height that the bullet-baseball combo rises after collision. Well, in order to figure out that height, we need to know how fast the bullet-baseball combo is going after the collision to figure out how high they rise, regardless of our approach doing that. That sounds like a conservation of momentum solution. P before equals P after. We ask ourselves, what objects, if any, have momentum before they meet or collide? The answer is only the bullet, whose momentum would be expressed by its mass times its velocity before the collision. After collision, the bullet sticks inside the baseball. It embeds inside it, so we have to combine the mass of our bullet plus our baseball. And we're looking for the velocity that this combination leaves at after collision. We go ahead and do the algebra. Pause if you need a moment to do that. And you should get an answer that's 33.3 meters per second repeating. All right, now we have a number of different choices that we could choose to solve this problem now. I'm going to choose a conservation of energy solution. And so we'll have EO equals E. What forms of mechanical energy are possessed by this system in the initial state? And when we mean the initial state, we mean at the moment the bullet and baseball are combined together, and that would be kinetic. So the bullet-baseball combo has kinetic energy, which transforms into gravitational potential energy at the top. The combination becomes at rest at the top, has no kinetic. We'll use the spot where the bullet embeds in the baseball as the base level, so no initial gravitational potential energy. And so all the kinetic that the combo possesses initially becomes gravitational potential at the end. We see here that we can cancel the mass of the combination. So we have 1/2 of our non-sig fig 33.3 squared equals 9.8 times H. We go ahead and solve for H, and we get that the bullet-baseball combo rises to 2 digits, 57 meters into the air. Our answer to number 7. Okay, let's move on to number 8. We have a billiard ball moving at 5 meters per second. There's velocity, initial velocity. Strikes a stationary ball, initial velocity 0, of the same mass. After the collision, the first ball moves at 4.33 meters per second. We're going to call that V1. at an angle of 30 degrees. So that's theta. We'll call that theta 1. With respect to the original line of motion. Find the velocity, v2, magnitude and direction, that's theta 2, of the second ball after collision. And in B, was the collision elastic or inelastic, and justify our answer. All right, the first thing that we need to do is give ourselves a good before and after diagram of this situation. And we're on the left-hand side here, we have a before collision diagram. We have a billiard ball of mass m moving at 5 meters per second, about to collide with another billiard ball of the same mass initially at rest. After collision, we're told the initial ball moves at 4.33 meters per second at 30 degrees to the original line of motion. And after collision, the second ball moves down, would move in a downward direction at an angle theta and final velocity v. What we should also do with this diagram is put in our components, since we know this is a glancing collision and we're going to need to add and conserve momentum of components at some point. So we have this component of our top ball here, which would be a 4.33 sine 30 degrees for its vertical velocity. And we have a horizontal velocity that would be 4.33 cosine of 30 degrees. For the bottom ball, we'll switch colors here. We have a vertical component that would be v sine theta, and we have a horizontal component that would be v cosine theta. Okay, let's just take it one step at a time and see what happens here. The first thing I did was I conserved momentum in the x direction. So what objects, if any, have momentum in the x direction before collision? Well, it's just the initial original ball, which has mass m and speed 5. Afterwards, that same mass m has a velocity 4.33 cosine 30 in the x direction, plus the bottom ball has mass m, which has speed v cosine theta in the x direction as well. We can see that there's an m in every term, so we can cancel it. And simplifying, we get v cosine theta equals 1.250, which is 5 minus 4.33 cosine 30. How many unknowns do we have here? Well, we have v as an unknown and theta as an unknown. Where are we going to get our second equation? Well, the problem here is that we were not told whether or not this collision was elastic or inelastic. In fact, it's what we're asked to find in B here. So that means we cannot necessarily conserve kinetic energy to get a second equation. Instead, what we need to look at here is that we potentially want to conserve momentum in the y direction just to see what we end up with here. So we're going to go ahead and do that. P before equals P after in the y direction. What objects, if any, have momentum in the y direction before collision? The answer is none. So there is no momentum in the y direction. After, our initial ball of mass m has a speed 4.33 sine 30, so its momentum is upward. Our other ball of mass m has a vertical component, a y component, v sine theta, and since that momentum is down, we're subtracting it. Once again, we can cancel m here because 0 divided by m is still 0. In solving for v sine theta, adding v sine theta to the other side, we get 2.165. So here we have two equations with the same two unknowns, v and theta, and we have an expression that has it equal to a number in both expressions. Any idea how we could solve this? Well, we've been down this road before in different unit. If we took the sine term and divided by the cosine term, we could eliminate v as the variable, and we know that sine theta divided by cosine theta is tan theta. So this would allow us to solve for the angle and then come back and use either equation to solve for the velocity. So tan theta would be 2.165 divided by 1.250. Theta itself would be the inverse tangent of that division. And by taking the inverse tangent, we get 60.0 degrees. Now that we know our angle, we can go ahead and use that angle subbed back into one of the previous equations. I chose the sine equation, the vertical equation. It did not matter which one we used. We should get the same answer either way. And so v sine 60 equals 2.165. Solve for v, and we get 2.50 meters per second. So there's the magnitude and direction of our velocity of the second ball after collision. All right, B asks us whether or not it was an elastic or inelastic collision and to justify our answer. Well, if the collision is elastic, that means kinetic energy would be conserved. So a way to test this would be to find the kinetic energy before, compare it to the kinetic energy after, and if we get the same value, then we know the collision was elastic. If we don't get the same values, in fact, if after we have less than we have before, then we know that kinetic energy was not conserved, therefore the collision is inelastic. So we go ahead and set up a k before equation, 1/2 m5 squared, and simplifying the numbers, 5 squared is 25, half of that is 12.5, so we end up with 12.5 m. We now go ahead and set up a k after equation, which would be 1/2 m 4.33 squared plus 1/2 m 2.50 squared. We simplify the numbers and combine our m terms, and we get a k after of 12.5 m. Well, since our k after is identical to our k before, what that tells us is that our kinetic energy was conserved, therefore the collision was elastic. Okay, it was a good problem on a glancing collision here, and a nice little problem on number 7, combining a couple physics concepts. More to come as you solve problem number 9 in class tomorrow.